Salutations, Internet. Good time zone. I hope everyone enjoyed the little break. It's been a minute since I last did one of these, at least from my perspective. If you're watching this in the future, I hope that you did take a break between videos. You got up, you stretched, you got something to eat, got something to drink, you socialized, didn't spend your whole day on the internet. I'm sorry if I'm calling you out. We're gonna move on now. So this is going to be the fourth video in the micro series of Lambert's problem and Lagrange coefficients. And I believe that it is healthy to pause at this point, take a step back, look at the new equations that we've got, and ask ourselves if these equations make sense. So that's what we're going to do today. We're going to take a look at these and see if they work. And to do this, I have taken the liberty of writing down some initial conditions. Well, at least what are supposed to be initial conditions for our system. These are largely the same as what we've dealt with in the past, except that these are in an Earth-centered inertial reference frame. And what that means is instead of r, theta, and I believe I was using z, so instead of the cylindrical coordinates, we have x, y, and z. So Cartesian coordinates, and it is based on the Earth as how we had described it in the Keplerian elements. So x is facing towards the sun during vernal equinox. I believe z is geographic north, but that part isn't important. What is important is that these are in terms of x, y, z, and not r, theta, z. So we're going to be taking a look at these, and we will be seeing what happens when we have a delta theta of 130 degrees. So we propagate the orbit 130 degrees in true anomaly, and we're going to see if everything makes sense. So in order to do that, I do want to point out that these are incomplete. This is the first set of Lagrange coefficients. There is an alternative set. It's not really an alternative set. It's just, this is incomplete. We'll be dealing with that next video. But we do have some things that we need. Like we need to know, actually I can sum it up. Let me zoom in so everybody can see what I'm talking about. So this right here is our future radius and our parameter, which we will be solving for both of these for the purposes of this video and this example. But well, before I get ahead of myself, so we need, wrong way. So we need P, which can be found here with the equation of h squared by mu. Mu is a constant, we don't need to worry about that. H, however, can be found here. So we need our radius and the tangential velocity. So because we have our radius confined to a single dimension, it is only in the x dimension, we only need to worry about the velocity in the y and z dimension. Because there is no velocity in the z dimension, we can have, and actually let me do this just so I can keep track of what's what. So we're going to start with our h being our r, 16,365.424, multiplied by our tangential velocity, holding no surprises for us, will produce 87,481.37399. Then, as pointed out, we use that to find p, so we square it and divide by... let me go ahead and write that out. 87,481. 37399. I'm mostly doing this for formality. Divided by 3.96 times 10 to the 5th. And that will give us... That will give us 19,199.67585 kilometers. I'm going to go ahead and underline that so I don't lose it, because we, as I pointed out, will be needing that feature. All right. There are two more values that I want to sort of write down, I guess. Well, that's not strictly true. There is one more thing that I want to do while I'm here, and I want to find what our radius and our velocity are going to be at the new angle. So the reason why I'm doing this is because I want to have something to compare it to when I get to the end. So let me do this. So we have R1 because we have R0. I like starting my indexes. I like starting my indexing at 0. And 19,199, 67585 over 1 plus 0.2 times the cosine of... So we have seen in the past that to get to this value right here, our initial theta has to be 30 degrees. So let me include that. We will have 30 degrees plus 130 degrees. Right? Our initial plus the delta to find what theta 2 is. And so, when you plug all that in, reach a value of 23,643.131 kilometers. No, I will use this. I will use green. And we also want the scalar velocity at that point, which is this equation down here. So we want the square root of 3.986 times 10 to the 5th times 2 over the radius. So I'm going to start with the radius. 23,643.131 under 2 minus 1 over a. And because this is a system that we've analyzed to death, we already know that our a should be 20,000. Well, not should be, it is 20,000. Our scalar velocity is going to be 3.713224804 kilometers per second. We'll go ahead and underline that as well. Now we're ready for the actual fun part with all of this. So I will scroll down to here. This is going to be fun to write up. So let's start with F. I will do one more. Zoom in. And we want this guy. So remembering that I like to index starting at 0. This is not the initial radius. This is the new radius, the second radius. So 1 minus, I'll tell you what, let me copy it over first. 1 minus cosine of delta theta. So we have 1 minus 23,643 new points 131 over P, which is 19,199 67585 times 1 minus the cosine of 130 degrees. So I'm going to do this slightly differently. Let's try to do that. Trying to budget some space for me. And we'll see just how far off I was. Anyway, now we're going to have F equals minus 1.022984292. All right, so we have our F value. Now let's get our G value. It's going to be this guy. I'll copy it over really quick. G is equal to R1, R0 sine of delta theta over the square root of P times mu. And that will look like the following. Oh, I don't have to scroll for this. So R1, 23,603.41. Sorry, 131. Only mistake I'll ever make. Times R0, 16,365.424 times the sine of our delta theta, which is 130 degrees. That is going to be over the square root of P, 19,199.67585 times, also under that square root, mu, 3.986 times 10 to the 5th. That's a weird looking 5 here. Let's try that. Do that. Down a little bit. Now we have G. That is 3,388.212351. Very nice. Now we're going to get to the messy one, F dot. And I need to remember to include the tangent because the number of times that I've done this set of calculations and keep forgetting that tangent. Anyway, that is going to be, I'm not going to copy the equation over because I'm going to run out of room. So I'm just going to copy over the values. Square root of mu over P. 6 times 10 to the 5th over P, 19,199.67585. That is then times 1 minus cosine of delta theta, which is 130 degrees. Again, that is going to be all over 19,199.67585 minus 1 over r minus 1 over r naught. So minus 23,603.1 inverted minus 16,365.424 inverted. Remembering the tangent, I very nearly forgot it. It's 130 degrees by 2. There it is. And that will give us an f dot value. All right, so our f dot is going to be minus 1.742866513 times 10 to the minus 4. It's worth noting that g has a unit of seconds and f dot has a unit of s to the minus 1. All right. For now, after all that, we now have g dot, which is pretty straightforward. It's the exact same as f, only with r naught instead of r. So let me write this over. For p, 1 minus the cosine of delta theta. That becomes 1 minus r naught, 16,365.424 over 19,199.67585 times 1 minus the cosine, 130 degrees, that's a g dot of minus 0.4002796,706. And this I will put a big green bracket around. All right. Now we have our Lagrange coefficients. Now comes the actual fun part of plugging them in. Let me do this. So R1 is going to be equal to minus 1.0298292 times our initial radius, 16,365.42400 plus G, 3,388, 212,351 times our velocity of 0.4556, 53455 and 0. All right. Now instead of writing this below, I'm actually going to write the result all the way over here. So our R1, we have an X value of minus 15,197.90214. We have a Y value of 18,111.68912. And our Z value is 0 because I wanted to make this easy on me. So not going to be dealing with the z values. All right. Now I will come back over to here, scroll the way back down. I'll do that. So we found our position. We now need our velocity. So it's going to be minus 1.742866513 times 10 to the minus 4th times, again, our initial radius, 16,365.42400, and minus g dot 0.400279676. That's our velocity of 0.4556, 5.3455, and 0. And similarly, I will be writing that up here. Give us a velocity in the x direction of minus 3.03464, and velocity in y direction of minus 2.139694979, and 0. I said 0. There you go. Kilometers per second. So we have a new position and a new velocity, but how accurate are they? Using Pythagoras, we can find a radius. Sorry, not a radius, a distance, which is going to be 23,643.382 kilometers, and similarly for velocity of 3.7131319.5 kilometers per second. And when you compare them to what we had found before, so our first attempt, or rather our initial attempt, using the methods that we are familiar with for the two-body problem, we are given 3,643. Let me just copy this over. I don't need to rehash this. All right, so I just copied over velocity and skipped over it because you didn't want to see me shaking the screen around. So now I want to take a look at the percent error for radius. So I want to know the percent error. How far off were we actually with this? Because these are differences. These are differences of hundreds of meters. And I'm going to do that by just doing the error formula. Which is going to be the same for velocity. So I'm just going to write the percent error for position first. So that error is 0.00106%. And the percent error for the velocity is minus 0.00250%, which is actually not that bad. That's really not that bad. Granted, it is still a difference of hundreds of meters, but we're not trying to navigate to it. We're trying to estimate an orbit for it. Now, one more thing that I want to do while I have your attention here is I want to determine the time of flight between the initial position and the final position. And for that, we're going to visit a different section of our notes. Let's take a look at... Okay. So, turns out there's several things that are going to be going on with this. First, we need to find... So if we're going to find out what the delta t is, we need to know what the difference in time is between position 1, or well, between the initial position and the final position. For that, we need to know what E is, and I would recommend using cosine E, but however you go about finding the eccentric anomaly angle, go ahead and do that. For me, I'm going to use the cosine because I like the cosine. So let me go ahead and write this down. Our cosine of, we want the eccentricity first. Oh, and this is for the initial. We want the eccentricity first, which we know is 0.2 minus the cosine of the initial value of 30 degrees over 1 plus the eccentricity times theta, 1 plus the eccentricity times the cosine of 30 degrees. And we want this in radians, so even though I have put in degrees, I will just convert it to radians after the fact. And really quick before I share my answer, let me go ahead and actually put in the correct sign. So our initial eccentric anomaly angle, 0.430771895. Again, in radians. So E0 from the periapse is mean motion. So a cubed over mu, square root of a cubed over mu, so 20,000 cubed over mu, 3.986 times 10 to the 5th. That should be a 5, not an S. Times E0 minus 0.2 times the sine of E0. And I'm just doing that to save me some time. So that will become 15,000. Sorry, not 15,000. I miscounted decimals. 1,555.47 seconds. Go ahead and underline that. And now I'm going to look for the eccentric anomaly angle of the final position. And remember that this is theta 2, not just delta theta, so 30 plus 130, 160 degrees over 1 plus our eccentricity times the cosine of 160 degrees. So that angle is going to be 0.2716214,001 radians. And again, effectively following this equation over here, except you're using E1, save me a little bit of time. pressed for time. That will be 11,798.84 seconds, which will give us a delta T of 10,243.37 seconds. Now, this last step may not be super obvious as to why we did it. I can assure you when we get to the end of the micro series, it will all start to make sense. So let me go ahead and write that up here, actually. Speaking of making sense at the end. So no, I don't want that. Delta T is equal to 10,243.37 seconds. So there you go. There is our little experiment with Lagrange coefficients. And for the next video, we're going to be one step closer to solving Lambert's problem. But I think that's enough for today. So, as always, I want to thank you all for stopping by.